Good. All right. So Chapter 8 is about subnetting IP networks. So this is where we start to look at how a network's construction allows us to logically organize its contents to better enforce security, to better troubleshoot information based on physical location as well as logical organization. So there's a couple of different pieces that are helpful through subnetting. So let me go ahead and jump down here. So we're going to look at how to implement a basic subnet in order to set up end-to-end connectivity in a small to medium business network. We're going to talk about how subnetting improves the things that I talked about earlier, communication, etc. We're going to look at calculation of subnets for a /24, /16, and /8 prefix. Now for IPv4, these are what we would call classful subnet divisions, meaning that they fall on the octet lines. Remember that we have 4 8-bit numbers that make up a 32-bit IPv4 address. So if we say 32 minus 8, that's 24. 24 minus 8, that's 16. 16 minus 8, that's 8. So that would be your divisions of the network and host portions. We're going to talk about how to implement an IPv4 addressing scheme given a set of requirements, which is not an uncommon thing you'll see. And then how to create what's called a VLSM, or variable length subnet mask structure, a flexible addressing scheme. We're going to look at how to implement a VLSM scheme for end users in a small to medium-sized network and how to implement. We're going to look at design considerations for IPv6 in a business environment, as well as how to implement, because IPv6 is, again, a little bit different. We're going from a 32-bit address to a 128-bit address. We don't have to deal with network translation the same way, so there are some changes. So let's get started with 8.1. So when we're dealing with what's called a broadcast domain, the area that is covered whenever a broadcast packet is transmitted, we have to think about why broadcasts get used. And traditionally, this is locational. It's being able to find information out about the network around us. And it's very similar to how we explore the world around us as people. You know, you use your senses, you use your eyes, your ears, etc., to be able to figure out what's going on. And then you look for signposts, pieces of information that allow you to identify where you are and hopefully where you're intended to go. You know, think about your first day of classes for the semester. You're always like, all right, am I in the right classroom? Is this the right instructor? Is this the right class? Am I bringing the right materials? Things like that. So in a standard LAN, devices will use broadcast to locate other devices via layer 2 to try and figure out the associated MAC address, and this is what is done through the ARP process. And then DHCP allows us to identify devices on a network that may need subnet masks, a default gateway, standard IP address, any of the essentials that we need to be able to communicate outside of our local network. So switches will go ahead and propagate these broadcasts across across all interfaces except the one on which it was received, because it wouldn't make sense to send something back to yourself. You're not gaining any new information that way. Now, if we're talking about a router, things like that, that broadcast is going to propagate slightly differently, but not by much. So whenever we're dealing with several users connected to the same link, meaning that they're all on the same switch or same tier, these broadcast domains can become problematic, because if we generate an excessive number of broadcasts, or if we generate broadcasts that are not resolving correctly due to pathing problems, we can negatively affect the network. So if we have slow network operations due to congestion, that can be not only because the amount of traffic that's on the network itself, but because every device that's connected has to process a broadcast packet, if even to say, I don't have to accept this, that this does not belong here. You know, broadcast packets, unfortunately, are kind of like people handing out flyers in front of a store. You know, it's just, they're just bunching them into people's hands. They're not even checking to see whether or not they're not filling up the trash can immediately behind them. So how do we solve this problem? Well, simply enough, we just start breaking it into smaller pieces. We create smaller subnets or subdomains that allow the broadcast domain perimeter to shrink. So instead of having 200 people connected to the same link, which is impractical anyway, we would go ahead and say, okay, let's go ahead and break that down by a factor of 10. Let's go ahead and have 20 people per area. So let's say the classrooms in any of our buildings. We traditionally don't have more than 20 devices in each of those. And even then, at that point, that seems a little bit crowded. We're closer usually to about a dozen to maybe 15. So this is so that we can manage those devices a little bit more accurately based on not only their logical structure, but their physical location. So here we have one broadcast domain with, quote, 400 users. We have 4 switches, all connected to a central router. So the 172.16.0.0, 400 users. It's a lot of information, right? So instead of doing that, let's go ahead and take our router and use 2 of our interfaces, G00 and G01, and split them off into 2 LANs. So we've got one subnet, 172.16.1.1 or 1.0, and 172.16.0.0, or 0.0, whatever you want to say. And we're going to say 200 users apiece. Now, granted, this is not a drastic change overall comparative to what I said, where we go from 200 to 20, but we are splitting it in half. If you ever get into software design, software engineering, you'll talk about sorting algorithms, things like bubble sort, things like that, merge lists. So the idea is, if you're trying to sort a list of numbers, the idea is break them into smaller lists. So we're going to go ahead and take the first list and go ahead and sort it, and the second list and go ahead and sort it, and then we'll merge them together one entry at a time. So there's a couple of different arguments about whether or not that's considered an optimal sort or not. But the idea here is pretty clear. We're dividing and conquering. Rather than saying, well, we've got 400 users, our optimum size is X, let's go ahead and divide it into that, we're just going to break it in half, and in half again, and in half again. And we'll see this propagate back up again when we get into VLSM and how we work with that. So subnetting improves overall traffic as well as overall performance because we are making sure that we're creating kind of this branching infrastructure to allow all traffic to flow back to that central point, what we call the demarcation point. This also allows administrators to implement policies such as which subnets are or are not allowed to communicate with one another. So you can have separation one to the other. Let's say that we have a public network we want to have available to guests while they're in our company building, guest Wi-Fi, that sort of thing. And we also have Wi-Fi for devices that are approved by corporate. Let's say that we have people who work for us who go out in the field, they're representatives, salespeople, things like that, and they need to be able to travel. Well, most often they're going to have devices that are wirelessly configured with dynamic configuration or whatever else when they're out in the world, but they may need a static address that they can connect to when they get here so they can access things like a company inventory or something like that. So in that point, we would want to have a subnet that was privatized for their use. So here we can see subnetting by device type in the bottom right, to where all of our standard PC hosts are on their own subnet, all of our printers are on another, and all of our servers are on a third. I'm sure you guys can see some benefits there, to where, let's say we have a long weekend, maybe we have like a July 4th thing, or maybe the current situation with the pandemic, to where there's a shelter-in-place option, not even option, a requirement. All of your hosts physically are probably not going to be active, but if you have an online presence, all of your servers will probably need to be active. So theoretically, you could go ahead and just shut down LAN 1 and focus on LANs 2 and 3, possibly only 3, depending on what products you need to handle. Communicating between networks, just above that, we can see that there's an administration LAN, a human resources LAN, an accounting LAN, and a student LAN. So imagine that this would be on a college campus. Administration would not need to necessarily have their information immediately shareable to any of the other 3 departments, and that's the same thing for students, accounting, etc. So this just allows us to compartmentalize a little bit. Let's say that the student LAN gets affected with a virus because somebody downloaded something that they shouldn't. Well, rather than dramatically affecting all 3 of the other LANs that are needed for the system to run, we just go ahead and shut down the student LAN while we go ahead and run antivirus and clear everything out and make sure all of our hardware is clean. And then the big one, save this one for last, subnetting by location. This is probably one of the more common ones that you're going to see. Simply breaking things down by the floor that it's on, and then of course maybe down to the room. Now granted, you'll usually have what are called IDFs and MDFs at that point, intermediate and main distribution frames. Your main distribution frame is going to be the primary point of access from your ISP. Again, a term I used a little bit earlier, the demarc or demarcation point. That's where the internal network and the external network split. Inside of that, with the IDF, the intermediate distribution frames, you can have a secondary router or a high-end switch that differentiates between floors. Inside of those floor switches, you can then have sub-switches for different room categories, etc. So that's a very common thing. Something you'll notice about these particular LANs in the example, I'm not sure how well you guys can see the resolution of the text, but LAN 1 is 10.0.1.0. Now we don't want to use the last octet for identifying the location in the address, because the last one traditionally we have as our host, because remember the network and host portions are read from left to right. So 1.0, 2.0, 3.0, etc. Now we could push this further and say instead we'll have 10.1.0.0, and then we can have the third octet be the room where something is located. So let's say that we have our normal classroom, 229. So if we were to have 10.2.29.0, that would be the network location for the 10 subnet, second floor, room 29. The network would be 0, and then all of our hosts would start at 1. Just as an example. So as I pointed out earlier, we have what are called classful boundaries that occasionally crop up. Those are commonly used. You can see here from the subnet masks in the table, /8 gives us a 255, /16 gives us a 255.255, and a 24 adds a third octet at 255 as well. Now, a convenient way of abbreviating this is to show addresses in terms of their subnet mask in binary, and then we can represent them in alpha characters using the N and H for network and host. So we can see here in the third column of the table, the division is 8 bits of network, 24 bits of hosts. Then we have a half and half, 16 and 16, and then we have 24 and 8. In certain shorthands as well, we may also say that if an octet is completely full of network or host bits, we can then replace it with the capital letter version, and that replaces the whole thing. So 8 lowercase n's could be replaced by 1 uppercase n. Same thing with the h's. Now, in order to create subnets, we do what's called borrowing of the host bits. So in the example of the /24, if we were to take this 25th bit, the first H bit, and convert that into a network bit, we would then be able to set another set of devices underneath that. We would have one that starts with a 1 and one that starts with a 0. So that's the 200 division that we saw earlier. Now, let's go ahead and use an example of subnetting the network 10x.0.0/16. We can define up to 256 individual subnets, with each subnet capable of connecting over 65,000 hosts. Because we're using the /16 mask, we know that the first 2 octets are going to be the network portion, and the last 2 are going to be for the host. So let's take a look at how this construction goes. We have the .10, or the 10 dot rather, which is the very first octet. That's going to be the same regardless. And then we have .0, .1, .2, .3, .4, .5, all the way up to .255. So these are all of our 256 individual subnets. So we have our 0 to 255, which is 256 individual options. Now, we have 10.0 going from 0.1, because we have to start at the first host, up to 255.254. We have to leave 1 at the end for the broadcast. And that is one subnet with 65,534 hosts. And we see that repeated through all 256 possible subnets. So the first 2 octets, as we will refresh, define our subnetwork, and the last 2 octets are going to define our host range. Now, obviously, as you shift going from a /8 to a /16 to a /24, the number of hosts and subnets will change. And of course, we want to make sure that we are balancing that with the needs of our particular network. Now, because of the number of hosts that is generated, a very comfortable 254 hosts, which is pretty simple for most basic networks, the /24 boundary is very, very popular. So let's just take a look at the first line of this table. 10.0.0.0. Okay, so that's our network. And then we only worry about the last octet as being our host bits. Now, if you have to connect more than 254 hosts on a single subnet, then obviously a /24 subnet mask is not for you. You'll probably want to back it up to a /16. Now, if you feel more comfortable with non-classed IP divisions, then of course you can go ahead and do a /23 or 22 or whatever you like. But until you have a bit more practice, this tends to be a much easier way to make sure that your subnets and your host ranges all line up. So this is what I'm talking about, classless subnetting. So let's take a /24 and subnet it even further, break it into smaller pieces. Oh, Sam, good question. So why would we go from 24 to 16? Because if we need more hosts, we have to do the reverse of what we're seeing on this slide. We have to go from, instead of borrowing to create more subnets, we have to create more hosts. So if we have 23 bits of network, that means we have 9 bits to set for the hosts. So instead of having 254, we would then have 510. Let me switch over to the whiteboard for a second. I can show you what I'm talking about. So let's go to, let's see, blank whiteboard. Okay. So let me go ahead and take the text here. So we're going to do 1, 2, 3, 4, 5, 6, 7, 8 dot. So doop, doop. All right. So there is your /24 mask. Let me go ahead and put that up here. Now, with that, I'm going to change my text color so it's a little bit more visible. We have these different subnets that are then possible, right? So we've got, let me go ahead and move this out of the way. I've got my screens to deal with. So if we've got these 3 individual octets, we've got 2 raised to the 24th power, or 65,536 subnets. Okay. This means that conversely, we have 2 to the 8, which is 256 hosts, -1 for network ID, -1 for broadcast. Okay. So that's our primary up here. That's the /24. Now, if I were to instead do a /16, and I were only to use 16 bits for my network instantiation, I can then say, okay, I've got my 1s, I've got my 0s here, I've got my 0s here. Okay. So that means now, switch to green for this, I have 2 to the 16 make sure I got my math right here. 2, 16. There we go. I did mess up here. Let's say 5. Okay. So this would actually, oh no, damn. /24 mask gives us 16.7 subnets, 254 hosts. Okay. With a /16, we cut it back to 65535 subnets, each with 65,533 hosts. Okay. So the idea here is because we take those 8 bits and move them to be available for hosts instead of being available for just the subnets, we change the power of 2 that we're multiplying by. So even something as simple as a /17 means that we now have a subnet mask that looks like this. Okay, so that means that now we have 2 to the 17th power in terms of the number of subnets that we have available. So 2 to the 17 is basically just double what we had before because we're doing extra power of 2. So that's 2, 17, 131,072. To and we'll get into this again in a little bit more detail there, but as you can see, just changing the 1 bit in the subnet mask to add the additional piece right here goes from about 65,000 subnets to 131, and it cuts our hosts from 65 to 32. So we're just shifting that balance each time. We're going from, if we go in the favor of the subnets, then we're doubling the subnet each time. If we go in favor of the hosts, we're doubling the hosts each time. So if we had a network where, say, we had to support 500 hosts per subnet, we could go ahead and move over to a /16 if we needed to. Now that's only if we needed to have that many hosts on a single subnet. That would be a very specific requirement. Does that help? Okay, just checking. All right, so let's go ahead and share application. Why is it not letting me switch? Some days. There we go. All right. So here we see a little bit more of an extension of this classless subnetting of just borrowing 1 bit at a time. So we go from a /24 up to about a /30. Now the reason we stop at /30 is take a look at the host count as we keep going down. What would happen if we got up to a /31? What would be the end result, you think? How many hosts would we then have available? Close, Colin. What we have to remember is it's not going to be just 1, because 126 is not a power of 2, 128 is. What we're doing is we're subtracting 2 addresses from this each time in order that we can support both the network ID and the broadcast. So when we get down to a /30, we have 64 subnets because we're using just the bits that are here. And then we have 2 hosts because we have 2 to the second power, which is 4, minus 2. Now, if we were to do 2 to the first power, that would be 2. And then if we subtract 2 from that, we would have 0 hosts. We would only have the broadcast and the network ID. We would have no address support for the host. So 30 is our cap. We can't go above that. But as you can see, we go up each time. 126, that's 128 minus 2. 62, 64 minus 2, 32 minus 2, 16 minus 2, etc. So as the number of subnets increases, the number of hosts will decrease. So something we see here is that the number of subnets that we divide out in each set here is only taking the bit after the class divide. So we go to the end of the 24 slash, and then we hit the 25, and that's only 2 subnets in this case. So if we want to follow that, if you go into our Netacad structure, you can go to the video demonstration for the subnet mask, and you can look at how to line up all of the ANDing and things like that. So this is largely what the video is going to show you, just kind of taking the network bits, representing them instead of being all lowercase n's, we just have one uppercase n for each. And then when we get to the borrowed bit here, we have the subnet n down here. So here we have our subnet bits. We're only borrowing one, so that's 2 to the first. Host bits, 2 to the 7th. We have to subtract the 2 for our broadcast and network ID, and that leaves us with 126. So we have 2 subnetworks with 126 hosts each, meaning that they go from 192.168.1.0 /25, because we are using that extra bit, up to 1.127. We have to leave off the 127 from 128 because we have to have a starter for the next network as well. So remember, because we're starting from 0, we go to 1 less than we would expect. Now, there is a technique that we use on occasion called the magic number. So to calculate the number of subnets that are supported, we go ahead and use the last value of the last one in the subnet mask. So here we'll go and take a quick look back a couple slides at this table. So here we see a /26, right? We have 62 hosts available. Okay, so that's because we calculated 64. Well, 64 in binary is 2 to the 6th, which would be right in the end of the host bit. So the /26, we have 128, 64, 32. So 64 is that second bit. That's the end of where we borrowed. If we go down to the /29, we have only 6 hosts because that's 8 minus 2. If we count over 128, 64, 32, 16, 8. So the last highlighted bit in this mask, the 5th one from the left or 4th one from the right, depending on how you want to look at it, is the binary representation of the number 8, 2 to the 3rd power. So that gives us 6 hosts in the listing. Trevor, those have not been uploaded just yet, but that will hopefully get done today. But yeah, no, that's definitely not off topic. That's right on board with what we're dealing with. So if we're using the magic number technique, if we're using a /27 subnet mask, then that means that we have 32 hosts per subnet. And thankfully, that also means that our starting address for each one is very easy to calculate, because we can just say, okay, we have 8 subnets here. There are 32 hosts apiece, so we'll just go ahead and start them at multiples of 32. The first subnet starts at 1.0. The next one starts at 1.32. The next one starts at 1.64, 96, 128, all the way up to 224, which is our maximum, 256, but we start at 0, minus 32. So that allows us to identify where all of our starting networks will begin. So if we have a /23, for instance, we're going to go ahead and take a 16 and move it into a 23. We're going to add 7 host bits here. Magic number is the last binary number in the mask, which is in the 2 place, 2 to the first power. So that means that we're going to have 2 hosts per subnet. So we'll go ahead and go to 172.16.00 through 172.16.1.255/23, and we have .2.0 and .4.0. That's the starters of our little subnets to be able to flip that back and forth. So here we have a subnetting example for a /25. We're going to borrow 1 bit, and then we have that 2 subnet value set up, either a 0 or a 1. And the new subnets will have the same subnet mask, because remember, the comparison between a 0 and a 1 and a 1 and a 1 is always going to yield 1, right? Now, if we have a situation over here on the right where we're borrowing a bit and we compare the 2 subnets, we see that they start at half of the maximum value. So if we have a 256 cap, we have the 1 at 0 and 1 at half of the maximum, which is 128. If we were to have 4 subnets, we would then have them in increments of 64. If we were to have 8 subnets, we'd have them in increments of 32. Okay. So if we're creating these 2 subnets, we have to have them assigned to an interface on the router in order to identify which direction traffic should be branching. So in this instance, we have router 1, and our G0/0 interface is going to provide a .1 here for our starting address. Remember that we cannot start at .0 because that's our network ID. And then if we go 1 above our network ID for the other side of the subnet, then that will be .129, and that's going to be on our G0/1 interface. So that means over here, when we look at these 2 devices, we see 192.168.1.128 is our network ID, and that's what shows up on the switch. On the other switch, we see 192.168.1.0/25. That's our other network ID on that switch. And then over here, the 128 is our network ID, the 129 is our router interface, and then the first host would be 130. So in this case, we have the what would normally be the first host ID being borrowed by the router interface. So if we want to create 2 equal-sized subnets, again, you can take a look at the video demonstration on Netacad. Basically just does exactly what we talked about. We take the maximum value, split it in half, which means our magic number for a /25 is the first bit in the 4th octet, or 128. So we go ahead and say 1.0, 1.128. So the subnetting formula, if you will, if you want to look at it more mathematically, is 2 to the n, where we have the number of bits that we have borrowed to calculate the number of subnets given. So if we have 192.168.1.0 /24 network, and we start borrowing, we look at the subnets thusly. 2 to the first bit, if we borrow 1 bit, is 2, so we have 2 subnets. If we have 2 to the second power, 4 bits, or 2 bits resulting in 4 subnets. 8 for 3, 16 for 4, 32 for 5, 64 for 6. So that allows us to get all the way up to a /30. So with the number of hosts, instead of calculating 2 to the n, which we had previously, we instead have 2 to the n minus 2. Now, I'm not really fond of how they have this listed in this particular graphic, because I don't think it makes a great idea of what it is, because a lot of people forget about the order of operations. So when we read this, we want to look at it as 2 to the n minus 2, but instead of having, let me see if I can grab can't grab a pointer, can I? So if we were to put parentheses around the 2 to the n, I would be much happier with that. Just so people remember, we're calculating the exponential function first. So if we have 7 bits, for example, in the host field, we're going to calculate that 2 to the 7th first. We're going to get 128, and then we're going to subtract 2. So remember, we're going to go ahead and calculate 2 to the n, and then we're going to remove the network ID as well as the excuse me, the broadcast ID. So now if we have 4 subnets and we're borrowing an extra bit, we now have 2 to the 6, or 64 IP addresses per subnet, subtracted out to 62. So we have our 6 bits here, so that's 2 to the n minus 2 to give us 62. And we have 2 to the n, the number of bits borrowed for the subnets, 2 to the second power, or 4. So network 0 starts at 0, 0. Network 1 starts at 0, 1. Network 2 starts at 1, 0. Network 3 starts at 1, 1. This allows us to differentiate between all 4 subnets. So we almost treat them as a separate column from the mask when we break off at the class line at the /24. And then we can see that each of these subnets will start at 0, 64, 128, or 192 because we're doing the divisions of the 256 possible values by 64. And they can all use the same mask, 255, 255, 255.192, which is 128 plus 64. So when you're calculating how those masks are going to read, just remember you're going to add those 1 values together that have been borrowed. So here we can see the structure of those networks. I don't know why they cropped off number 3, but that's the same general structure. So we can see it's 1.00, 1.01, 1.10, and the other one will be 1.11. Okay. And then we go ahead and assign them normally. So we see here we've got our 4 subnets. We've got our interface here .1, interface here G01.65, and then we've got our 129 on this side, which would be normally starting our first host address on network 2, connecting over to 130 on the second router and creating the opposite side. So if you want to take a look at your videos again for /26 and /27 subnets, those are available on Neticat. So make sure that if you're confused about this in any way, go ahead and take a look at that. I tried to include a light text representation of each so that way you kind of make sense of what you're looking at. So subnetting a 16 or an 8 prefix is a little bit different, simply because you're dealing with usually much larger numbers of hosts, dealing with the number of host bits and things like that, so the exponentiation gets a lot larger, a lot faster. If we have a /16 prefix, /16 subnet mask, and we want to create 100 subnets, let's go ahead and take a look at the structure there. In order to get to covering 100, we need to look at the largest value that just covers it. So does 2 cover 100? No. 4, 8, 16, 32, 64. Okay, we're getting close. We're at 2 to the 6th. But 64 doesn't quite cover it, so we have to go over a little bit, what's called a minor amount of wastage, at 2 to the 7th. So 2 to the 7th covers 128 individual subnets if we borrow that out. So we take a /16 and create a /23 from that. So we have a 0, 1, 10, 11, 100, etc., going all the way up to 7 ones, 1111, 1110 for our initial subnet. And then each of them, because we have a host bit left on this side, we're able to go 9 host bits in order to produce our hosts. So 2 to the 9th would be, let me see, 512, I believe, so 510 individual hosts inside. Yep, still got the math in my head. So you can see here 2 to the n for our host bits, 2 to the 9th, minus 2 for our broadcast, and for our network ID. So there's our address range for each one. Now, creating that subnet, if you want to see that again visually, watch the video. You can see that there on our Neticat site. Now, if we wanted to create 1,000 subnets, we would have to start further back. We couldn't do that with a /16. We'd have to go back to a /8. So we have to do the same process. How do we get to 1,000 in binary? Well, it's the same problem we have with hard drives. We don't equate 1,000 to 1,024, but the closest representable value we have to use. So we got to go up to 2 to the 10. So if we're borrowing 10 host bits here, that means we still have 14 on this side, 8 and 6 for our hosts. So now we've created what's called a /18 because we've got 8 here. We're borrowing 8 plus another 2, so that's 10. So this becomes a /18 network creating 1,024 subnets. So that means that each subnet will then support 16,382 hosts per subnet. 16,384 minus 2. So 2 to the 14. When I told you guys at the beginning of this course that you were going to have to play a lot with powers of 2, definitely true. Something that I've gotten really comfortable with is just making sure that I'm aware of 2 big values, just kind of as my place markers, which is 2 to the 10 and 2 to the 7th, just to make sure that I'm staying on top of my inside or outside boundaries. So 2 to the 10, pretty easy because we've got 10 fingers, is 1024, and then 2 to the 7th is 128. That's the maximum length of an 8-bit value. Now the reason I say those 2 are easy for me to remember, and that's what I use to kind of stay on top of this, is that anytime you want to modify a power of 2, you just double it or cut it in half. So if I wanted to figure out what a 12 would be, 12 bits, then I would just go ahead and double up 10 to 2048 and then again to 4096. And that gives me my 10 bits borrowed. If on the other hand I wanted to get down to like a 4-bit borrow, I would take my 7, 2 to the 7th, 128, and cut it in half. 64 is to the 6th, 32 is to the 5th, 16 is to the 4th. So just getting kind of comfortable with those powers of 2 is going to be very helpful for you with this. Now, if we want to subnet across multiple octets, cutting across, in this case, we've got 300 equal size subnets of 20,000 hosts each, starting from a 10,000/8. And we can look at that. And that is leading us into the idea of subnetting based on requirements. So we're given a list to say, this is what we need our networks to have. This is the structure that we have physically for these rooms. This is the number of hosts we need per sub, etc. So again, just kind of looking at our table, if we have a /25, we know that we have 2 subnets and we have 126 hosts each. So maybe we have a situation where we don't necessarily need a large number of hosts for each section, but we need to be able to apply group policy or other management structures very easily. So we'll need to have a large number of subnets at that point. So we could then, if we're using a /24 anyway, we could very easily use a /16. We're going to get in and say, okay, let's use a /27. We need 8 subnets, 30 hosts apiece. We can go ahead and borrow 3 bits in order to create our subnet. So that's just an example of, again, finding based on host requirements, how many subnets do we need to support? We have to cover the number of subnets, but by the smallest possible amount. If we need 1,000, 1,024. If we need 514, we're still going to use 1024 because 512 will not cover what we need. So we have to remember that we have to support the minimum number of requirements, but no more over that overage. So if we have a situation where we have host devices used by the engineering department need to be tucked away in one network, management needs to be tucked away in another, human resources, sales, all of these need to be separated, then we would say, okay, well, we need 6 subnets. Or maybe each area needs a different set of subnets, blah, 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 blah. But the real trick is we've talked so far about equal-sized subnets. Well, what if we needed different-sized subnets? So let's say that, let's say that in LAN 1, engineering, they need 30 hosts. In LAN 2, they need 23. In LAN 3, they need 40. And LAN 4, they need 35. And in LAN 5, they need 10. Okay? So for LAN 1, how many bits are we going to have to borrow to cover that? Got 30 hosts. That means that we're going to need how many host bits at least? So 2 to the 7th would be 128, Sam. So that's a little bit of overkill. Just a wee bit. So back it up just a bit. Take another stab. How many bits do we need to get to a power of 2 that would exceed 30, but by the minimum amount? What's the closest power of 2 that's near 30? There you go, Colin. 5 bits. So again, 2 to the 0 is 1. 2 to the first is 2. Then 4. Then 8. 16. 32. No. That's the whole point, is that we got to practice. So no apologies needed. So 2 to the 5th power is 32. So we need at least 5 host bits to cover LAN 1. What about LAN 2, 23 hosts? Are we able to reduce that by any amount, or do we still have to stick with 5? Is the next power of 2 down from 32 able to cover 23 hosts? Still 5. Very good. What about LAN 3? Now we have to cover 40 hosts. Well, 32 is under 40, so we can't cover that. So that's where we got to have 6 host bits to cover 64 hosts. Same thing with LAN 4. They're over 32, so we got to cover 6 for them. And then LAN 5 only needs 10, so we could use 4 bits at that point for them. So we've got, if we look at these LANs, LAN 1 needs 5 bits, LAN 2 needs 5 bits, LAN 3 needs 6, LAN 4 needs 6, and LAN 5 needs 4. Okay, so if we look at this and we know that we need at minimum 6 host bits for each one, let's go ahead and take a look at each of these. So we've got our network portion and our host portion. We can divvy it out to say, okay, 10 host bits there, and we've got 1,000 hosts total. And then we could theoretically break that apart, because if we look at the sum, 30 plus 23 is 55, plus 40, which is 95, and then another 35, which is 130, and then LAN here is 140. So only 140 hosts are actually required. Now, again, we're going to have interfaces for other stuff as well. But we can see here that we're borrowing our bits to break them up into multiple subnets. We've got 5 separate ones each. And we can use those smaller values as we work. So now, what we do in order to separate these things out is we've got .16.0.0/26. So we've borrowed 2 host bits. Again, look at that top bit there. We've got, instead of 8, we've got 10. So we've got .0, .64 going across, and then we've got 16.1 over here on LAN 3. We've got 16.0.128 and .192 over here. And then we've got our interfaces here. We've got 2.64, 2.128, 2.192, and 2.0. So you can see that our individual LANs are using the .0 interfaces, and the router links are using the .2 interfaces in order to differentiate, so that way we're still setting them out. So we've technically got, because of the connections between each, we've got 9 total subnet interfaces here. Now, variable length subnet masking tends to work a little bit better for this type of situation, because again, what we looked at when we were trying to structure who needed what, how many subnets we needed, we were looking at equal numbers of hosts per. So look at this particular situation. We've got a network that's broken into 8 subnets. We've got 4 buildings, 3 WANs to go from site to site, and we've got an unused or available listing down at the end. We've got 8 subnets because we borrowed 3 bits, and we've got 5 hosts. So 32 minus 2 is 30. And we take a look at the network portion. We've got 25 hosts, 20 hosts, 15 hosts, and 28 hosts. So if we look at building C, it's only using half the hosts that we need. 2 to the 5. So each WAN subnet, because we're only going from one to the other, so we've got 2 links, is wasting 28 addresses. So that's not positive. We want to avoid that. And 84 addresses in total are just going unused. Pretty depressing, right? So we've got 28 times 3. So we've got 60 plus 24. So VLSM kind of uses more of what I was talking about earlier. Instead of having 30 hosts each in 8 subnets, we can then say, well, let's take these subnets and split them into smaller pieces to better use the numbers we already have. So in this case, we've got a single subnet of 30 broken up into 8 subnets of 4 each. So here we have subnet 7, and we're going to break that into smaller pieces. So we're going to take the /27 that was there, and we're going to convert that subsection of it to a /30. So we're going to have the same network, but using 2 different subnet masks. So when we borrow those 3 bits, we've got the 1.1, which is the original subnet we were working with, and now this is the sub of the subnet, identified by a colon. And we've got 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. We need 8 subnets of the 8th subnet, so that gives us 3 bits again here. And then our host portion allows us to find our 2 bits here. We can have 4 individual hosts. So remember that we have our WANs here, site A to B, B to C, and C to D. Each of them only need 2 hosts. So now it's perfect because we've got 2 hosts on each of these subs. So there's our A to B and B to A, and then the repetition for each one, splitting those links. And then now we're only wasting 2, 4, 6, 8, 10. 10 addresses instead of 84. 74 addresses that we can assign for something else. So as long as the address range does not overlap, you do not have to have all of your subnets be the same size. Again, there's a lot of videos in this chapter, but I did want to kind of go over it verbally. If we take a look at the graphic here in the bottom right corner, you can see this subnet being split up. We have the original network of 192.168.1.0/24. Easy network to use. We have our 8 bits of host portions here, so we can go ahead and do 2 to the 8th, or 254 minus our 2 network and broadcast IDs. And then they go ahead and say, well, no, let's go ahead and borrow 2 bits and split it into 4 subnets. We've got 1.0, 1.64, 1.128, and 1.192. Well, we can go even further by taking that last subnet and borrowing 1 extra bit, creating 2 subnets, and then we have 5 bits for our host. So again, this is all the same network, 192.168.1.0. We're just changing how the subnet mask is read over the network ID. So we create these networks within networks. So now once we've gone through and we've practiced and we know what our VLSM addresses are going to be, we've got building A, B, C, and D. Increments of 32 each on the host portion. So 20.0, 20.32, 20.64, and 20.96. And then inside of that, we've got 224, 228, and 232. Remember that each of these only have 2 hosts each for our WAN links. And we assign those from R1 to R2, R2 to R3, R3 to R4. And we can assign those serial interfaces in order to make sure that we're providing the correct connection between routers, as well as providing the correct subnet to the host. So for example, let's go ahead and take a look at R2. The text may be a little bit difficult to read, but it says IP address for gigabit 00, which is the interface that's going directly to building B's hosts, is 192.168.20.33. So what is the 20.33 interface? What is the purpose of that IP address? So 20.33 is one above the address here for building B, the primary address. So that primary address is the network address, right? So that said, we have our network address. What is one above the network address in any subnet? You're thinking at the opposite end, Colin. That would be the .63 address in this case. What's the opposite of the broadcast address if we're talking about our reserved numbers? First host address, very good. So again, the 32 is our network ID, our .63 would be our broadcast, and the 20.33 would be our first host address. So the interface for that first host address to make sure that all of that network traffic that's on building B's subLAN can actually talk to the router has to be that first interface. Very good. Notice that the subnet masks between gigabit 00 and the serial interfaces are different. So 224. Okay, so 128 plus 64 is 180, and then 192, and then another 32 is 224. Okay, good. So 224 to 252 would be another 32, so that's that extra bit that we borrowed. So we notice that subnet allows us to shift down from 27 to 30, so that way we can go ahead and make sure that we're separating those networks by the subnet mask. And then let's say we've got 226 being our interface to S00, and then 229 being the interface to 001. So 226 is essentially connecting to the 224 address on R1, and 229 is connecting to the 228 address on R3. So that we have those links. Again, we're just trying to avoid wastage, so VLSM allows us to have that tiny section at the end just for our WANs. So here we can see the subnet breakdown, R1 to R2, R2 to R3, R3 to R4, and then we have our unused ones at the very end. Now, if we wanted to do VLSM using a 172.16 network with a /23, we've got 6 subnets total. One for 200 hosts, one for 100 hosts, one for 50, one for 25, one for 10, and then 4 point-to-point networks. So in order to do all that, we would go ahead and start breaking it down like this. We take /23 and break it in 2 in order to get the 256 network. So we're going to take the first split, and we have one network for 256. So that checks off our 200 hosts. But we still have these others. So we split the 256's second half. So we go from 0.0, and now we create 1.0/25, and that gives us 128 hosts. But we still need to divide it further. So we're going to take the next one, and we're going to take the second half of the second half and divide it again, and again, and again. And then when we get down to 16, instead of breaking it down into 8, we're just going to go ahead and take 4 point-to-point networks for 2 hosts each, so 4 by 4, giving us our breakdown here. So again, we're just, in this particular instance, we have a VLSM that's very clean. We're able to say that we can take divided by 2, divided by 2, divided by 2, and just keep working our way down. If we wanted to, if we had 200 hosts, 100 hosts, 50 hosts, and then we had 3 or 4 networks that all were 10 hosts each, we could use multiple 16-bit subnet masks instead. Yes, Sam, remember, that's the idea, is that we need to use our powers of 2 because that's what the subnet mask represents. So if we were to try and use 128 instead of 256, we wouldn't have enough. We wouldn't have enough hosts to cover it. If we had 257 hosts that were needed, 256 wouldn't be enough. We'd have to go up to 512. So again, it's all about how many hosts need to be supported and we have to look at the difference between decimal and binary. What's the smallest binary number that allows us to cover our requirements? So again, like with 50 hosts, we couldn't use 32 because 32 wouldn't be more equal to or more than 50. 128 is more than 100, but not 64 wouldn't work because that's not more than 100. So that's what that is. It's just making sure that we have our ability to cover the number of hosts we need. A little bit of wastage is okay, but we don't want a large amount. So now let's talk about a little bit of address planning. We've looked at how we structure these things logically, but we need to make decisions on how each of these are going to be established. How many hosts do we need? How many subnets do we need? How are these host addresses going to be assigned? So when we're doing this planning process, we have to think about how to prevent duplication, how to monitor security and performance, provide control, access. Everybody's got to have a unique address within a network. Now, granted, with different subnets, that allows a little bit of variation, but not by much. We need to make sure that we are establishing controllable access, which usually means static addresses for things like WAN links or servers or things like that. We also need to make sure that the segmentation is performed correctly so that if we have something that's generating excessive amounts of traffic, we can go ahead and shut it down or at least isolate it and figure out why that particular link is so hot. Now, of course, we have to look at what requires an address. The end devices, the end user clients, those are going to be ones that we need to think about a lot because that's the majority of our population on the network. Now, in order to save time and errors, we can use things like DHCP, but DHCP also has some issues of its own, meaning that it's difficult for security to properly exclude certain devices through blacklisting. So it's easier to do whitelisting and going ahead and providing static addresses for all devices, but that consumes a lot of time, especially for very large networks. Now, if we change our subnetting scheme, we also have to go in and change the DHCP server to reflect those new subnet masks, the new what's called address pool. IPv6 clients use what's called SLAAC, SLAAC, in addition to DHCP version 6. As I said, servers should be configured statically, and if there is a private address, they need to be translated publicly. Intermediary devices, so if we have like a switch, things like that, we need static addresses for those as well. And then the gateway, our primary router to exit the network, that also needs to be configured statically so that it can be accessible from the internet via an IP address, not necessarily just resolution through some kind of portal. Now, IPv6 again is a little bit different. We talked about that with SLAAC just a second ago, but it's not concerned with conserving address space because the address space for IPv6 is massive. Subnetting in this case is based on building a hierarchy so that we can keep things organized. So what would seem to be a slightly lesser focus for IPv4 is the primary focus for IPv6. A link local address, meaning the local network to which you're connected inside the switch for a particular group of computers, is never subnetted. Now, what's called your global unicast ID can be subnetted. So traditionally, your global unicast address is going to consist of a global routing prefix, the first 48 bits. A routing prefix is going to allow us to identify a device anywhere on the planet, kind of like having a country code or an area code for a phone number. The subnet ID, 16 bits, is going to be a rather small identifier for a subnet just because there's so many different interfaces that could be provided. And then 64 bits for telling us who you are, you know, the actual license plate that gets stamped on your NIC. So here we see a single subnet increment going from 0 to 1 to 2 creates 65,500 each time. So you can see that not only are there 65,000 subnets, but each subnet contains a massive number of hosts, 2 to the 64. So if we're setting this up, we'll go ahead and establish our different subnets based on the requirements of the document. So if we need to set up 5 subnets, we're just going to go to ACAD. Again, this is just the default address, just kind of an established one that we use a lot. ACAD:1 /64. The double colon represents what? What do we recall about the double colon with an IPv6 address? Represents zeros, absolutely. So that means that the double colons show that we've got 4 hextets up at the front. We know an IPv6 address is 8 8 blocks of 4 zeros apiece. So we've got our 64 block going through the end, because our characters are in hex, but the binary representation is 16 per block. So we can see that the first half of the address is what's concerned with the network ID. Everything else is just blank. So we've got 2001 0db8 ACAD 0001. That's our first subnet. 0002, 0003, 4, 5, etc. And as you can see in the bottom right corner, that's kind of the packet tracer command line interface there, assigning those subnets. So we see ACAD:1 :1. So that's that first host ID for that particular subnet. 2 :1, 3 :1. That's our, again, that's just kind of a stylistic default. There's nothing mathematically that we run into with that requires it. You could have 2001:6 AC12:1, but it's not. It would be considered out of convention. It would not be considered practical. Other technicians would look at it and be like, "Why are you doing that?" So that is Chapter 8. Lot of information to be covered, I will admit, but thankfully it's the kind of stuff that it gets easier over time. So what I would recommend is just go in and take a look at those videos on Netacad and practice with it. Just kind of play with it. Pick a number between 25 and 30, and just figure out mathematically, okay, how do I do these? And then once you've got one set, the VLSM, to where you take 256 hosts, break it into 2 128s. You take the second 128, break it into 2 64s. That's a really good example of how to play with VLSM as well. And that's something that I always like students to kind of get familiar with also, because there's a lot of help in that. So let me go ahead and just show you again. So we got this. So let's say that this is 256 total addresses, 254 hosts, right? So if I were to take a circle like that here, give me the ellipse. Make it a little bigger. Let's say I go ahead and take my line, I cut it in half. So now I have 128 total, 126 hosts. I can split it again. Hosts. So here we can see that I've got 5 subnets, one for 126 hosts, one for 62, one for 32, and then 2 for 16. And it doesn't have to necessarily be in descending order, though that is often something that we we recommend. I could very easily take this out, go ahead and remove that, and take the, let's go ahead and grab the line, and we'll go ahead and split that in half. And we'll split this one in half again. So now I've got 8H, I've got 4H there as well. So it's just going to kind of depend on how you structure it yourself. This is going to essentially be the same idea. It's just however you try and arrange it. Very easily could I take the 64 up here and split that again, and then have 3 of 32, 1 of 16, 1 of 8, 2 of 4. However you want to look at it. That's it's just going to depend on the structure that's necessary based on your particular requirements document. Okay, whoever's got what's going on. Okay.